Again, without further ado, it is my utmost pleasure to give you another iteration of the ML Theory guest speaker series. Today, I'm personally very delighted to welcome Frederik Kunstner to our community, who will give us a talk about why does Adam work so well and how you have heavy tail imbalance in language modeling. So again, as per usual, a bit of context about the speaker. Frederik is a postdoctoral fellow at INRIA in Paris, working on the intersection between machine learning and optimization. His research focuses on identifying why methods that work best in practice outperform classical algorithms. Frederik's paper on the EM algorithm received the Best Paper Award at AI Stats in 2021, and his research has been supported by an RBC Borealis Fellowship. He received his PhD at the University of British Columbia in 2024, and his MSc and BSc from EPFL. Now, I'm personally very excited because I told Frederik this before we started. This paper in particular inspired a large part of my master's thesis that I wrote last year, and the work was extremely detailed and very, very thought-provoking. So despite the slides, I do recommend that you read it because it is really a fantastic piece of research, and it is a great pleasure to have you, and I'll leave the floor to you.
Thanks for the amazing introduction, and thanks for the invite and accommodating the fact of doing this on Friday because of the NERDS deadline. I hope it went well for everyone and their supplementary material. So yeah, let's dive into it. I'm going to be talking about why Adam works so well. And on the audio, everything is fine? Yeah, all right. So starting with the basics, what's Adam? You might have heard of it if you've trained any kind of deep learning model. It's the most cited algorithm for neural networks. Over 200,000, it passed that in December last year during NeurIPS, and it's probably 10K more at the moment. I haven't updated the screenshot. But despite it being almost the default method to train any kind of deep learning model, we don't really know why it works so well. So if you look at the more classical optimization people that are working in ML, people like Ben Recht, who have posted on their blog that Adam is the most cited algorithm in optimization, that the proof is wrong and unpassable. So that starts as well. And other ideas like the blog of Francesco Rabona, where he describes how we arrived to algorithms like Adam as a result of evolutionary pressure, where we try to find optimizers that work for the models that we're currently trying to train, and we're trying to tweak the model so that they work with the optimizers that we have. And somehow by almost a genetic algorithm running through the optimization for ML community, we've arrived at Adam and it works. But that doesn't really answer why it's such a good algorithm. And the reason why we care is that it works super well. And on training LLMs, like transformer-based models, typically you have a 10x, 100x better performance with Adam just in terms of training loss. You don't even have to look at generalization, just training goes so much faster with Adam. And so what we're interested in is trying to understand why and how optimization works in deep learning. Going through the trial and error evolutionary algorithm argument is fine to explain why things end up working. Well, that we have things that work, but it doesn't really tell us what problem we've solved by coming up with those algorithms and what the bottlenecks are. So in this talk, I'm going to go over some insight that we can get into the optimization bottlenecks that are present in fitting deep learning models by studying what problems and optimizer work well together, specifically Adam and transformers. So to get everyone on board, thought I would give a quick recap of Adam. So we start with gradient descent. We just have some step size alpha and gradient g, and we take a step in the direction of the gradient. I'm assuming that's all fine for everyone. And then if we want to be a bit more fancy, we add momentum where we have a moving average of the gradients as we're doing optimization. And that works better. We can prove that it's very gives faster performance on quadratics and extrapolate this to bigger models. But then comes Adam. And in Adam, we accumulate a second momentum buffer with a moving average, where we accumulate gradient squared, where all the elements, the operations on vector are performed element-wise. And then we divide our gradient by the square root of this second order moving average. All right, So why does this update work? There are different ways of looking at it. One way of simplifying the algorithm a bit is to look at it as sign descent, where the idea is if you remove the moving averages, as in you set the beta parameters to 0, what you end up with is just the gradient divided by the square root of the gradient squared, everything element-wise again. So this gives you +1 or -1, or the sign of the gradient direction. Another viewpoint that's been more argued in the papers like Adam and other papers of that era is that this was doing an approximate second order method that would be similar to computing the diagonal of the Hessian and using the inverse of that up to square root. And this would be better because of reasons that are similar to why we use second order methods like Newton. Now, the slight problem with those two arguments is that if those are valid approximation of Adam, then this tells us that second order methods are kind of like behaving like sign descent, which doesn't make too much sense because one is using less information about the gradients by just taking the sign, and the other is supposedly using second order information about the function, which we're not computing in Adam. So if this is confusing at this point, I think this is normal. It is for me too. And the goal of what I hope to get with the talk is giving you a bit more insight into why those updates can make sense. All good for now?
Yep, all crystal clear. I don't think there's any questions in the chat for the moment.
Oh, nice. Little cute thumbs ups on Google Meet. Cool. All right. So what we can prove about Adam in theory is kind of limited. If you look at the optimization papers that work in the classical settings we have in optimization, like smooth, Lipschitz function, convex, the guarantees are worse than for plain SGDs. And so the question becomes, what should we prove? Because the assumptions that we have for classical optimization theory, they obviously don't apply for deep learning, where Adam is most useful. So can we maybe learn something from experimental results where we have some models where Adam does better and come up with assumptions that more reflect what the problem looks like so that we can have a better description of the difficulties of optimization? And one nice observation is that while Adam does much better than SGD on language data or language transformers, the gap between the two algorithms is much smaller on vision. So you can find a bunch of papers looking at the difference in generalization capabilities of SGD and Adam has this reputation of having a worse generalization than SGD. But this is very much a generalization issue. It's not a training issue. Both of them can get the error to essentially 0 as fast as you want. There's not a big performance gap between the two. Whereas on transformers, it's just not possible to use SGD and get to a reasonable training loss, even disregarding generalization, in a reasonable amount of time. So maybe there's something about transformers that fits Adam much better that we've fixed by using Adam. Can we try to understand what it is? So to give you some idea of the typical assumptions that are used for the analysis of gradient descent or the stochastic variance, which motivated some of the hypotheses that people have come up with. A typical one for the convergence of gradient descent in the deterministic setting is that your Hessian is bounded. This is nice because it lets you put a quadratic upper bound on your objective function, and if you minimize this upper bound, which is guaranteed to give you progress, then this recovers a gradient descent step. The equivalent that the additional assumption that we need for SGD is some assumption on how the noise behaves. For example, the variance is bounded. And so this lets you argue that if gradient descent does something, like going to the minimum, SGD is going to do something similar to that and also converge. People have, obviously, both assumptions are wrong on neural networks. And even on quadratic, the bounded noise is not a very good description. But we worked with simplified assumptions to try to get a simple theory out of it. But if they're wrong, how can we which one is more wrong is not clear, and how should we change them to better model deep learning training. So there's been a few relaxed assumptions that have been proposed. One of them was relaxing this noise assumption. Instead of having bounded variance, people have noticed that on language data, the variance of the gradient is typically much larger. So what I'm showing on the top right is a histogram of the difference between the stochastic gradient and the average one. And on the left, you have CIFAR10 and image dataset, where things are roughly normally distributed. But if you go to language, there's a heavier tail where you can have some stochastic gradients that have a very large error. And so an alternative assumption for this is, okay, if we assume that the noise is actually heavy tail and the variance is infinite, but we have some control over higher power, for example, so that it still doesn't explode too much. Under those kind of assumptions, SGD no longer works because you have an infinite variance. And so if you take one step, the expected error at the next step is infinite. This is not a great description of what happens on neural networks either, because the loss doesn't go to infinity. But something like the variance being too big for SGD might give us some insight on what's happening. And those kind of assumptions let you argue that methods like doing gradient clipping, normalized gradients, or sign would reduce the variance because you're doing normalized updates, and so you cannot have arbitrarily large error, and this would help optimization performance. Another line of work is looking into relaxation of the curvature assumption. Rather than assuming the Hessian is bounded by some constant, people have noticed that the magnitude of the Hessian and the magnitude of the gradient evolved throughout training, and typically they evolve similarly with each other. So this is a plot showing the correlation between the gradient norm and the magnitude of the Hessian throughout training, with the color being the iterations. And so this motivated an alternative assumption where you say, okay, the Hessian is bounded by a constant plus something that can grow with the gradient. And the intuition there is, if your gradient is large, then your Hessian might also be large, and so you cannot trust your gradient too much, and you would need to take a smaller step size when your gradient is large. So this also gives you a reason to argue why SGD would no longer work in the setting, because you cannot just take a constant step size. And again, methods like clipping or normalized gradient descent would work better. And to motivate something like sign descent, you can have a version of this assumption that hold like per coordinate, where you assume that there's a correlation between the diagonal of the Hessian and the magnitude of the gradient element-wise. So those are two of the assumptions that have come up in the literature to try to understand or justify why algorithms like Adam, doing gradient clipping or taking the sign or normalizing your update, why those things work. And they target two very different problems that you might have with an optimization problem on deep network. One of them is more focused on heavy tail noise. The other argues that there's a correlation between the gradient and the Hessian. And it's not clear which one is more relevant, why those things appear, and whether they're really the problem that Adam has fixed. So what we did was try to test those assumptions and come up with, find a feature of the problem that would lead to those kind of observed behavior. In a first paper we did sent to unclear, we found that noise does not appear to matter much. The way we did this is by training smaller language models on small data set like PTB, but training them in full batch. And so you use the entire data set to compute the gradient at every step. And if you do this, you still have a huge gap between the performance in Adam and gradient descent. Here in black, you have gradient descent with and without momentum, Adam with and without momentum on the first beta one. And the gap can be even bigger than in the stochastic case. So this indicates that you don't need heavy tail noise or stochasticity to explain why Adam is better. There should be an explanation that holds even in the deterministic setting. And an interesting observation we made through those ablation experiments is that normalization alone is not enough to give you as good a performance as Adam. And in the stochastic setting, sign is garbage. But once you go to full batch, sign, descent, and Adam behave very similarly. So one intuition for this is that the moving averages that you have in Adam might be quite important to have stability when you have very noisy gradients, but that the main benefit also appears in the deterministic setting, in that you have a different step size for each coordinate, and that's the bit that helps you most. Normalization alone helps a little bit in the deterministic setting, but doesn't get you all the way down. Okay, so if noise is not the issue, we need something that could explain this in the deterministic setting. Maybe this idea that the curvature and the gradients are correlated has something to it. Especially because we see that sign has a good performance, so you would need to do something element-wise rather than just normalization. But it's not clear why this correlation would emerge, why this would have more impact on language, or what kind of simple model would have this behavior. And so in our next work, what we showed was that you can get those behavior if you look at the class imbalance, and specifically the heavy tail class imbalance that we have in text problems. So what I mean by this is that when we do language modeling, we do next word prediction. And because it's language, we have many rare words. So in language, typically, if you look at the relationship between the rank of how frequent a word is and its frequency, it goes according to Zipf's law, where the probability of the kth word appearing is roughly 1/k. And this heavy tail, because we're doing classification for the next word, becomes a heavy tail in the class frequencies that we're trying to predict. The way this plays into optimization is kind of interesting. So here I'm showing the training loss with gradient descent and Adam on transformer, small-ish, a few layers. And here I'm showing the frequencies of the classes on, I think this might be PTB, where the color coding indicates that we're splitting the data set into 10 subsets that each have 10% of the data. So the first group, which is in dark blue, might have like 3 classes, which are the most frequent words in the data set. And the last maybe 1,000, 5,000 classes here correspond to the least frequent tokens that we see in our data, and we group all of them together. And what we look at is how the loss evolves on each of these subsets. So what I'm plotting here is a zoomed in version of the loss of SGD. If you were to sum or average all of those lines, you would get the black line over here. And what we see is that SGD is going much slower on low frequency classes, but on the high frequency ones, it's doing very similarly to Adam. So this motivated our hypothesis that the slow training that we see on SGD is because SGD is slow on low frequency classes. And because we have this heavy tail behavior in text data, the fact that we have many samples from low frequency classes, like each word is rare, but there are many, many rare words. And so on average, they contribute a lot to the overall loss, making gradient descent slower overall. All right, so that was the main observation. Now, to figure out whether imbalance really causes the problem, we ran to a bunch of ablation studies. So for example, possible confounders, this could only happen on large scales. What we showed is that this already appeared on a very small transformer, like 2-layer, 2 transformer modules, 2 attention modules on PTB, being a much smaller setup, and we already see this behavior appearing there. A nice thing we're having this behavior appear on small models is that we can check whether the problem is due to stochasticity. Because we have very rare words, maybe the problem is that we see rare words too little when we do subsampling to really learn them. But no, we get the same behavior when we train with full batch deterministic on transformer models. Maybe it's other properties of transformers or language data that lead to this behavior and not just class frequencies. So to check this, we went to other models where GD and Adam typically do very similar. So we took a ResNet on ImageNet with 1,000 classes. On the top right is the training on the normal problem. And we changed the problem by subsampling the classes to have this parallel frequency of 1/k. And when we do this, we see a gap appearing between SGD and Adam that's much bigger than in the uniform case. So it's not only due to language data. You can make this appear on images if you make the distribution heavy-tailed. And finally, as a simplest example we could come up with, a linear model where you take the inputs being completely uniform between 0 and 1 in high dimension, and y being heavy-tailed, so still classes. This problem, there's no relationship between x and y, but x is still high dimensional enough that you can fit the model perfectly, which is complete overfitting. There's nothing to learn, but it's still a valid optimization problem. And there we see a very similar behavior, where GD struggles on the low frequency classes, Adam fit everything. All right, any question on the experimental setup?
I have one question. Did you try do the vision task, let's say, with like vision transformers, so that it wasn't like like convolutional architectures, and do the same findings hold roughly?
Yeah, we have a ResNet and we have a VIT, and they behave similarly.
Okay, thank you.
Yeah. The VIT are a bit difficult to train depending on which version you take. The original architecture described in the VIT paper is notoriously hard for SGD2, but there's been a new version, well, a paper that's like how to train your VIT by the same authors, I think. And that's the version we used, and we saw no difference between SGD and Adam there. That might vary depending on which flavor of VIT you use.
Okay, cool. Thank you.
So to give you some intuition as to why gradient descent would struggle on a problem with class imbalance, consider the case where you have a bunch of functions, like C of them, and they're all the same, like a half W square, and you're trying to optimize this. If you take gradient descent with a step size of 1 on one of these functions, you get to the minimum in one step. But now, instead of minimizing each of them individually, we're going to minimize their average, which are weighted, and I'm calling the weights of these the frequencies. Now, what happens there is that gradient descent on the parameters associated with one of those functions, the step size is going to get multiplied by the frequency. And so on the low frequency ones, it's going to go much slower. But on the high frequency one, you cannot increase the step size to counteract that effect, because otherwise you're going to have divergence. Whereas if you do sign descent, then the magnitude of the gradient doesn't matter, and you do the same update for all of these. So on this toy problem, we have a similar kind of behavior that appears, where gradient descent struggles on what I'm calling the low frequency classes here, and Adam and sign descent do well. Of course, they're not necessarily converging, they can oscillate, but the big difference is how they handle across different frequencies. So this could be interpreted as some form of preconditioning that sign descent is doing, taking your function that has a very different curvature in different directions and making it more uniform. And if we look at the specific problem, the Hessian is diagonal, and the values of the Hessian along those diagonal are given directly by the frequencies, which, if you have 10,000 classes, would vary by a factor of 10,000. And the gradient, at the same time, is also multiplied by those frequencies. So if the weights that you start with at initialization are roughly on the same scale, the gradient and the magnitude of the gradient and the magnitude of the Hessian are going to be correlated at the start. This is not true for the entirety of the landscape, but it's likely to be true for the path that we take during optimization. And so what we showed is that a similar behavior appears, well, first on linear models. So here we are just fitting linear models, so a big matrix that goes from D dimension to C output classes. And what we look at is the magnitude of the gradient and the magnitude of the Hessian block that correspond to each classes, so that we can isolate the effect of frequency. And what we see is a correlation that emerges between the magnitude of the gradient and the trace of the Hessian, which are going to be related through the relative frequencies of those classes. So on the linear model, this looks like this, where there's no correlation at the start. The gradient starts correlated with the class frequencies, but the Hessian is roughly uniform across all classes. But once you start training your model, you get this alignment effect that appears. And the gradient and the Hessian become correlated. This is on the toy linear model I was talking about, but we can see the same over the trajectory of the last layer of a large language model. So just looking at the last layer, we see also this correlation emerge. And to justify why it disappeared, we showed as a little proof of concept that if you assume that the model becomes correct in the sense that it predicts the correct class with some fixed probability p, and it predicts the incorrect classes with roughly uniform probabilities, then you can show that the blocks of the gradient and the Hessian roughly scale with the class frequencies, where x bar and h bar are just the average data that you see for your model. So this heavy tail class imbalance, we've shown that it gives a deterministic mechanism to explain why something like sine or atom would outperform gradient descent. And it also captures one of the main differences between vision and language, where language problems are typically very uniform and they're curated to be uniform. There are some data sets that people are trying to capture the long tail of language of vision problems, but the main ones that people are training for benchmarks are all like no longer MNIST, but CIFAR and ImageNet. And so this heavy tail class imbalance can also be reproduced on very simple problems where we can analyze what happens. It's consistent with other results that have appeared last year. You might have seen the Adam mini paper or the deconstructing Adam ADA layer papers that have come out. This is a figure from their paper. They're arguing that the Hessian structure of the network is mostly block diagonal for the Adam mini paper, but within each block, they're very uniform. And so you can essentially, you don't need a single learning rate for each parameter. You can average all of those for each parameter block. But the interesting thing from those studies is that the place where they couldn't reduce the number of step sizes per layer is in the first and the last layer, where you have one of the dimensions being the vocabulary size in your dataset. And for those, you need a different learning rate for each parameters, for each vocabulary that would have a different frequency. So this is consistent with observation that one of the main benefits of Adam would be in adapting to class frequencies. Most of what I had for the empirical side. Any questions so far?
There's no questions in the chat, but if anyone would like to ask a question, feel free to unmute yourself.
Please do. Otherwise, I'll move on. So one thing I've been kind of vague about is how we formalize this. And what do we mean by heavy tail imbalance? In the high-level description I gave you earlier was a large imbalance in the class frequencies, but that you also need lots of sample from low-frequency classes so that they have a large impact on the overall loss. And it would be nice if we could prove that sign descent is better. The problem with this is that most convergence rates that are in the literature for sign descent get worse in large dimension. Problem being is for sign descent, the problem has to somehow be aligned with the parameter space you start, because you're doing things per dimension, which makes a lot of the convergence rate that we derive very loose. And so they get not that informative when you're in large dimension, which is bad for deep learning because dimension is often very large. Even if you only think of dimensions to vocabulary size, you have 10,000 at the minimum different tokens that you're trying to learn. So in the paper we just submitted to NeurIPS, we came up with a toy model where we can make those arguments a bit more formal. So if the main problem that we're studying is in the first or the last layer, where our model has to deal with one-hot encoding of the data or classes, then one possible model to try to formalize this would be to think of a linear bigram model. So here I'm thinking of x and y as just one hot encoding of a token in d dimension. We have n samples, and we're trying to learn just a linear model that maps from x to y. So we're trying to predict the class of the next token y given x with just a linear regression problem. And what we would be trying to learn with this matrix W is the conditional probabilities of j given y, y given x. To model the heavy tail imbalance that we have in text, we're going to assume that the frequency of each word follow a power law with power alpha, where alpha is 1 typically in text, but we're interested in figuring out how this how the differences in power law lead to different optimization dynamics. And we're also going to assume that if you look at the conditional distribution of the next word and you rank them according to how frequent they are, they also follow a very similar power law. So this would be true if your data was completely IID following a power law distribution, but this also seems to fit relatively well real data. This is the word frequencies and the conditional frequencies on open web text with BP tokenizer, where we have a good fit for the 1/k word frequency following zip law. And we have a reasonable fit for the conditional frequencies as well, except that it seems the vocabulary size for the next word is a little bit shorter, which makes sense if you think that having condition on one word limits the range of words that you're going to be able to follow that up with, especially for tokens, which won't be part of a word that often go with another one. With this toy model, this idea that large imbalance plus lots of sample come from low frequency classes, we can start to play around with this. So if we have alpha equals 1 as in text data, this would be our baseline. But if we change this alpha, we can make it smaller than 1. As we go to 0, it becomes completely uniform. So as we decrease alpha, we have less imbalance, but we have heavier tails in the data because we can't ignore the last 10% of classes. They're still going to have a lot of mass in here. But as we increase alpha, we increase the imbalance between the most and the least frequent classes. But because we increase this imbalance, there's much fewer samples that are coming from low frequency classes. And so if we try to train a model like this with data that follows those distribution, we see that alpha equals 1 is almost worst case, well, out of those 3. If alpha is small, gradient descent still works. If alpha is big, gradient descent still works. But alpha equals 1 is this worst case scenario. And what happens if we look at the loss for each of the samples? So on the x-axis, I've ordered the samples in the data by frequency. If alpha is small, the imbalance is smaller, so we can fit roughly all the data. When alpha is big, we can't fit the very low frequency classes, but they're so small that they don't matter for the overall loss. But for alpha equals 1, we have this where both phenomenons are the worst, where we can't fit the low frequency data, and there's a lot of it, leading to slow performance. And this problem is bad for ZIP's distributed data, so for alpha equals 1, as we have in text, and it gets even worse with dimension. So as we increase the size of the vocabulary, the performance gets worse and worse if we have ZIP's distributed data, whereas if alpha is bigger than 1, things seem to converge and not depend on dimension too much. And things still get worse with dimension, but slower if alpha is smaller than 1. So this motivated to look into scaling laws for deterministic optimization. Typically, scaling laws are thinking about how, like in the online learning setting, where you get fresh data at every step, how many samples are you going to need to fit a model of dimension D? What we're thinking is, okay, if we do deterministic optimization and we increase the vocabulary size, how should we increase the runtime to get the same accuracy at the end? And especially, does this depend on the algorithm and comparing sign and gradient descent on this type of setup? And the problem is phrased as, okay, we want to reach a relative error of epsilon, where we normalize because otherwise the starting and the final loss depend on the vocabulary size. How many iterations t do we need to get to epsilon error? And what we find is that for gradient descent, this scales as d to the 1 minus epsilon. And so if we want a very small error epsilon, this scales roughly linearly in d. And so if you double the size of the model, you're going to have to double the number of iterations you're going to do with gradient descent. Whereas for sign descent, this scales like square root of d, giving you a much better performance when d is very large. We confirmed this on empirical data to check that the assumptions that we made for the frequencies, the conditional frequencies were okay. And we have a reasonable fit for the real data performance. This is still on a linear model. But on dashed, you have the asymptotic convergence rate as dimension go to infinity. This is what we would expect to happen. And even though we're in finite dimension and with real data, we have a relatively good match. And the scaling with dimension and relative error also seems to follow those trends, that the difficulty scales with the square root of the vocabulary size for sign descent and almost linearly with dimension for gradient descent. So this gives a setting where sign descent scales much better with dimension than gradient descent, specifically on zip distributed data, which is a nice result given that most of the results on sign descent would have predicted a worse performance with dimension. Those kind of scaling laws give a real problem where sign can outperform gradient descent, and how much faster it is roughly square root of the vocabulary size. So if you have a vocabulary size of 10K to 100K, it's going to be 100 to 300 times faster if you want to reach very low error. Want to point out that this is not due to just having the input be one-hot encoded or the input being sparse, as is often justified in the AdaGrad or sign descent literature. The distribution that we pick matters, and the convergence of sign descent gets much worse than that of gradient descent if alpha is bigger than 1, where gradient descent doesn't depend on dimension, but sign descent definitely does and scales badly. This was work that followed very much in the line of work of the scaling laws that have appeared in recent years, but they typically focus on the regime where alpha is bigger than 1, because they are modeling something where as you increase dimension, the dynamics become more and more converge to something without having to scale time, which seem to empirically be valid if we scale the dimension of the inner layer of the network. What we were looking instead is what happens if you scale like the first layer, if you increase your vocabulary size, where alpha equals 1 might be the better fit to describe what's happening and capture this dependency between runtime and dimensionality. Right. So that was mostly it. We're getting to the conclusion slides. What's next after this? Maybe this can help us develop better models for optimization problems. The imbalance that we've identified seems to be a very important feature on how different optimization algorithms perform on simple models like linear models. It'd be nice to have something that is a bit closer to realistic things like deep models, including momentum, doing the stochastic case, dealing with cross entropy rather than the squared loss. But this imbalance seems to be a key property to explain why algorithms like Adam or sign descent do better. If frequencies are the problem, obviously this comes to question of, is there a better way to fix it than doing sign or Adam? Can we estimate those frequencies differently or change the initialization or normalize a different way so that we don't need to rely on Adam or other tricks to perform better? Like, is there a change to the architecture that would make language transformers trainable with gradient descent? And of course, if you've followed the optimization literature, especially on Twitter this recent months. People are excited about Shampoo and Muon, which seem to perform much better on the inner layers. And one hypothesis for this would be that the frequencies are, the problem with the frequencies in the first and the last layer are axis aligned, that one of the dimensions that you have is which word it is in the vocabulary. So a diagonal preconditioning would fit that quite well. But once you go into the inner layer, everything gets mixed into the hidden dimensions, and you need to do non-diagonal preconditioning to solve that problem. And finally, there might be other problems or bottlenecks that Adam has fixed that might have already been ironed out in Vision with architecture changes and initialization tricks, or changing the activation functions, that we're still in the process of figuring out with language models, which has been, I think I've seen a few papers coming out on arXiv in the last week or two that were proposing this. Presumably they've been submitted to NeurIPS, and we'll get some of those insights in 6 months. All right, that was it. I want to give a thank to all my collaborators on this. Those are the 3 papers I told you about today, mostly about the first one being about the noise, second one being the empirical investigation of heavy tail class imbalance, and the last one, which we just submitted to NeurIPS on the toy linear model. It's going to appear on arXiv on Monday, if everything goes well. All right, thank you very much for your time.